Welcome back to the deep dive. You know, we hear this a lot. People get through those first PyTorch tutorials, they build that MStep classifier, feel pretty good.
That first success.
Exactly. But then there's this wall. You think, okay, that was neat, but how do I take this skill and build something, real, something that actually goes out into the world?
That gap is definitely real.
Yeah.
It's the jump from a controlled experiment to, well, production-grade machine learning.
And that's what this deep dive is all about. Bridging that gap.
Right. Our mission today is to give you a shortcut, really, to understand the thinking behind the architecture, the low-level stuff that matters, the whole end-to-end process you need for building, optimizing, and deploying serious ML systems with PyTorch.
It's about getting beyond just knowing the API calls.
Yeah. It's understanding why. Why do things this way for performance, for scalability, for making something you can actually maintain.
And we've got some great resources guiding us. There's a really comprehensive report mapping out the whole PyTorch production path, from the basic tensor right up to deploying transformers, plus a solid summary hitting the key questions.
Should be good.
So get ready for hopefully a few aha moments. We're diving into what comes next, the practical stuff that really makes a difference. Let's get into it. Okay, foundation first. Tensors. Everyone using PyTorch knows Torch. Tensor. It's the basic data structure, right? Like a NumPy array, an n-dimensional array?
Pretty much, yeah. Conceptually very similar.
But what's the killer feature for deep learning? Why PyTorch tensors over NumPy?
The GPU advantage. That's the crucial difference. NumPy is fantastic for CPU stuff, but PyTorch tensors, they're built to run computations directly on GPUs and other accelerators too.
And that means speed.
Serious speed. For the kind of math in modern neural nets, you're often looking at like 50x speedups, maybe even more. It makes GPUs pretty much essential.
50 times faster. Okay, that's huge. But say you've got your data on the GPU. Are there still, hidden traps, performance pitfalls people don't see coming?
Oh, absolutely. A common one is just using .2 device and thinking you're done. The problem often isn't just moving the data. It's the CPU-GPU data transfer bottleneck.
Bottleneck? How so?
But the fault, that copy operation is synchronous. Your CPU kicks off the transfer, and then it just waits for the GPU to finish receiving it.
So the CPU is twiddling its thumbs.
Exactly.
Yeah.
And while the CPU waits, your super powerful GPU might be sitting idle, just waiting for the next chunk of data. It's like having a race car stuck in rush hour traffic.
Okay, so how do we clear that traffic? How do we keep the GPU fed constantly?
The trick is asynchronous data transfer. It's a really powerful optimization. You need two things working together.
Okay.
In your data loader, you set pin memory true. And when you call that to CUDA, you add non-blocking true.
Pin memory. What's that doing?
Think of pinned memory or page-locked memory as like a special express lane on the CPU side. When the data loader puts tensors there, it allows for something called direct memory access, or DMA.
DMA?
Yeah. It lets the CPU start the transfer to the GPU and then immediately go back to loading the next batch of data without waiting.
So it's overlapping the work.
Precisely. CPU loads data while the GPU is busy computing. That overlap maximizes your hardware use, keeps the GPU humming.
That makes total sense. Concurrency is key. Now, another subtle thing with tensors, memory layouts. You hear NCHW, which is the default, right? Torch.contiguous format.
NCHW, batch, channels, height, width.
But then there's NHWC, torch.channels/last. Why does this layout difference matter in production? Seems like a small detail.
It seems small, but it ties directly into hardware optimization. Deep learning libraries, like NVIDIA's cuNN that PyTorch uses under the hood for things like convolutions on GPUs, they're often highly optimized for the NHWC layout.
Yeah.
And newer hardware, like tensor cores on NVIDIA GPUs, also prefer NHWC.
So if my data is in the default NCHW,
the library might be doing hidden transpose operations behind the scenes, switching to NHWC, then doing the math, then switching back to NCHW.
Extra work, costly work.
Exactly. If you explicitly use channel/last format for your model and tensors, you align the data directly with how the hardware wants to process it. You skip those hidden transposes.
And that means speedups.
Significant speedups, especially for computer vision models, without changing the model's actual logic at all, just aligning the data format. It's a neat trick.
Definitely a pro tip. Okay, let's move to Autograd. The engine of learning, you called it. Its core job.
Autograd is fundamental. It's PyTorch's automatic differentiation engine. It figures out how to calculate all the gradients needed for optimization.
The gradients you need for gradient descent, how the network learns?
Exactly. It automates that whole complex process.
And it uses this dynamic computational graph, or define by run approach. What's special about that? How's it different from, say, older frameworks.
Yeah, that's a key PyTorch feature. The computational graph, or the record of operations, isn't fixed beforehand. It's built dynamically as your code runs during the forward pass.
Defined by run.
Right. And the cool thing is, this means you can use standard Python control flow, like if statements or for loops, inside your model's forward method, and they can actually change the graph structure from one run to the next.
Okay. Unlike static graphs, where everything had to be declared up front.
Exactly. That gives you immense flexibility, especially for research or models with tricky logic.
Makes sense. Now, the classic training loop steps, optimizer.zeroGrad, loss.backward, optimizer.step. That ZeroGrad called, it trips people up. Why do we have to do that?
Yeah, it seems weird at first, but it's actually a deliberate design choice.
Yeah.
And a useful one. PyTorch, by default, accumulates gradients whenever you call loss.backward.
Accumulates, so it adds them up.
Yes. If you didn't call ZeroGrad, the gradients from the current batch would just get added on to the gradients from the previous batch and the one before that.
Which would mess up your parameter updates?
Totally. But this accumulation behavior isn't a bug, it's a feature.
How so?
It's essential for techniques like gradient accumulation. Imagine you want to train with a huge batch size, but it doesn't fit in your GPU memory.
Right.
You can do several forward passes with smaller batches, call backward after each to accumulate the gradients, and only then call optimizer.step and ZeroGrad. It simulates a larger batch.
Clever. And you mentioned RNNs.
Yeah, it's also useful in recurrent neural networks for accumulating gradients across multiple time steps. So ZeroGrad is just your way of saying, okay, start fresh for this optimization step.
So understanding accumulation turns a quirk into a tool. What about using Autograd beyond that basic loop? Controlling things.
Absolutely. For inference or validation, when you don't need gradients, you wrap your code in with torch.autograd.
Why do that?
It tells Autograd to stop tracking operations, saves a lot of memory and speeds things up because it's not building that graph history.
Okay, essential for evaluation. What about detach?
Detach creates a new tensor that shares the same data, but is, well, detached from the computation graph. Gradients won't flow back through it. Useful if you need a tensor's value for something else without affecting backpropagation.
Got it. And you can even do more complex math.
Yeah, Autograd is powerful enough to compute higher-order derivatives like Jacobians and Hessians. Super useful for scientific computing or advanced optimization methods.
Okay, solid understanding of Autograd. Let's talk nn.Module. This is the base class for basically every model in PyTorch. But it's more than just a box to put layers in, right?
Oh, definitely. It's the foundation. It acts as this smart container for your layers, your parameters, buffers too.
Yeah.
It handles a lot of the bookkeeping for training, saving, loading.
And the pattern is always define layers in init, define the data flow in forward.
That's the standard way, yes.
Now, I've seen people call model.forwardX directly sometimes. Why is calling model X the right way? What's the difference?
That's a subtle but really important one. Calling model X actually invokes the call method of the nn module.
Okay.
And call does more than just run your forward method. It handles crucial background tasks, things like registering and running hooks, which we'll get to, managing internal modes like training or evaluation.
Hooks. So if I call forward directly, I bypass all that.
You do, and that can lead to weird bugs. Hooks won't run, maybe things like dropout or batch norm won't behave correctly because the module doesn't know if it's supposed to be in training or evil mode. Always use model X.
Good to know. That call method is doing important work.
Definitely. Especially if you start using more advanced features or custom modules.
Speaking of custom stuff, another nuance. nn parameter versus a plain torch. Tensor, they both hold data. Why the special class?
This is all about telling PyTorch what it should learn, what it should optimize. N-parameter is actually a subclass of tensor, but it has a special flag.
Okay.
When you assign an n-parameter as an attribute of an n.Module, like self.weight in n.parameter init, the module automatically registers it.
Registers it how?
It adds it to the list that model.parameters returns, and that list is what you feed to your optimizer. So the optimizer knows to update these parameters.
So if I just assign a regular torch tensor as self.sumTensor torch.random.
The optimizer won't see it, it won't be trained. This is useful if you need state in your module that shouldn't be optimized, like maybe a running counter or a fixed buffer, or like a cached hidden state in a custom RNN.
That's a neat distinction, trainable versus non-trainable state.
Yeah.
And speaking of state, how do we save and load models correctly, especially those non-trainable bits, like maybe the running mean and batch norm?
The standard mechanism is the state edict. It's just a Python dictionary mapping names to tensors. It holds all the n parameter values.
Okay, that saves the weights.
Right. But for state that isn't a parameter but should be saved with the model, like those batch norm running means and variances, you use register buffer.
Register buffer.
Yeah. You say self.register buffer, running Miller's, torch.zeros. These buffers are included in the state dict, so they get saved and loaded correctly. But crucially, they are not returned by model.parameters, so the optimizer leaves them alone.
Perfect. So statict handles both parameters and registered buffers. All right, nn.Module gives us the model structure, but a model needs data, fast, especially at scale. Let's talk data pipeline, dataset, and data loader. Why is this so critical in production?
Because your amazing GPU is useless if it's starved for data. An inefficient data pipeline is often the real bottleneck in training. Dataset and data loader are PyTorch's tools for building fast, scalable pipelines to keep that GPU busy.
And for custom data, which is most real-world data, you make your own dataset class. What are the essential methods you have to implement there?
3 key ones.
Yeah.
Init, which runs once when you create the dataset. Good for setting things up, like loading file lists or metadata.
Okay.
Then len. Simple. It just needs to return the total number of samples in your dataset. And the most important one, getItem self, IDEX. Given an index IDX, this method has to load and return the actual data sample, like an image in its label, probably applying some transforms too.
So init, len, getItem. Got it. And then data loader wraps around that data set. What's its magic for speed?
The data loader handles batching, shuffling, but crucially parallel data loading, using multiple worker processes.
Ah, the num workers argument.
Exactly. Setting num workers greater than 0 is your first weapon against GPU starvation. It spins up background Python processes to load data using getItem in parallel.
Circumventing the GIL, the global interpreter lock.
Precisely. This lets your CPU fetch and pre-process data while your GPU is chewing on the previous batch. You get that vital overlap.
And finding the right num workers is key.
Yeah, it needs a bit of profiling. Too few, and your GPU waits. Too many, and you might overload your CPU or memory. But getting it right is a huge performance boost.
And this connects back to pinned memory, right?
Yes. For the absolute best throughput, you combine numworker 0 with pin memory. True in the data loader. That gives you parallel loading and asynchronous GPU transfers. Max efficiency.
Okay, that paints the full picture. What about data sets where samples aren't all the same size, like sentences and NLP? How do you batch those?
Great question. That's where the Coley-Teffin argument in data loader comes in. You can pass it a custom function.
A custom function to do what?
To define exactly how a list of samples from getItem should be combined into a single batch. For NLP, your Coley-Teffin would typically pad all the sentences in the batch to the same length, maybe sort them by length for efficiency, and then stack them into tensors. It gives you fine-grained control over batch creation for tricky data.
Okay, we've covered the bedrock. Let's move up to building something state-of-the-art, the transformer. Why focus on this specific architecture? It seems to be everywhere.
It really is. The transformer from that attention is all you need paper just revolutionized NLP, and it's making huge waves in computer vision and other areas too. Understanding it, maybe even implementing parts of it, is fantastic practical experience because it uses so many core PyTorch concepts together.
Right. And it famously doesn't use recurrence like RNNs, so how does it handle the sequence, the order of words?
That's where input embeddings and positional coding come in. Since the main mechanism, attention, looks at all words at once, it doesn't inherently know if a word is first or last.
So you have to tell it.
Exactly. You add positional encodings to the word embeddings. Usually these are fixed sinusoidal functions at different frequencies. It injects information about the absolute or relative position of each token in the sequence.
Clever. Okay, then the heart of it. Multi-head self-attention. You called it the engine. What's it actually doing? Can you give us an analogy?
Okay, imagine you're reading a sentence. For each word, self-attention lets that word look at all the other words in the sentence, including itself, and decide how relevant each one is to understanding its own meaning in context.
So each word is paying attention to others.
Right. Technically, each word creates a query, Q, and compares it to the keys, K, of all words. This gives an attention score. These scores then weight the values, V, of all words, to produce the output for the original word. It's learning context.
And the multi-head part.
Instead of doing that QKV calculation just once, you do it multiple times in parallel, with different learned transformations for Q, K, and V each time. It's like letting the word ask different kinds of questions or look for different kinds of relationships simultaneously.
Looking through multiple lenses, like you said.
Exactly. Each head focuses on a different aspect, and then you combine their outputs. It gives a much richer representation.
Fascinating. And these attention blocks build up the encoder and decoder stacks.
Yep. The encoder stack processes the input sequence. Each layer has that multi-head self-attention, then a feed-forward network, with residual connections and layer normalization around both. The decoder stack is similar, but it has two attention layers.
Two.
One is masked self-attention on the output sequence generated so far masked, so it can't cheat by looking ahead. The other is cross-attention, where it attends to the output of the encoder stack, letting it connect the input and output, plus the feed-forward layer residuals and norms.
That's quite intricate, so building it from scratch teaches you a ton.
A huge amount, yeah.
But for production, you'd probably just use PyTorch's built-in modules.
Absolutely. Torch.nn transformer, transformer encoder layer, transformer decoder layer. They are highly optimized, tested, and ready to go. Building from scratch is for learning. Using the library modules is for production efficiency.
Makes sense. So understanding the architecture is one thing, but training these big models effectively requires more than a simple script. Let's talk about the professional training loop. What makes it different?
It's about structure, reproducibility, and managing complexity. You typically organize code better, maybe separate functions for train epic, validation epic, orchestrated by a main training function.
What are the key ingredients?
Centralized hyperparameter management is crucial, maybe using config files or tools like Hydra, proper setup of your loss function and optimizer, of course. Comprehensive evaluation, not just loss, but relevant metrics for your task, like BLEU score for translation. And critically, checkpointing.
Ah, saving your progress. Why is that so vital?
These models can train for days, even weeks. If your run crashes or the machine gets preempted, you absolutely need to resume from where you left off, not start over. Checkpointing means regularly saving the model state and the optimizer state.
Optimizer state too. Why?
Because optimizers like Atom have internal state, like momentum estimates. If you only save the model weights, you lose that optimizer state, and resuming training might not perform as well initially. Saving both lets you restart exactly.
Lifesaver for long runs. Now, managing all these runs, different hyperparameters, maybe architecture tweaks, it gets complicated fast. That's where experiment tracking comes in, like MLflow.
Oh, yeah. Trying to track runs manually with spreadsheets or naming conventions.
Yeah.
It's a recipe for disaster. You lose track of what worked, what didn't, which code version produced which result. It becomes impossible to reliably reproduce things.
Been there. So how does MLflow help?
MLflow gives you a dedicated place to log everything about each run. You start a local server easily with MLflow A. Then in your training script,
You add some logging calls.
exactly, you wrap your training logic in MLflow.startRun.
Mm-hmm.
Inside that, you log hyperparameters with MLflow.logparams, log metrics like loss or accuracy over time with MLflow.logmetric, and save output files like plots or config files as artifacts with MLflow.logartifact.
So it creates a detailed, searchable history of every experiment.
Yep. Centralized, organized, and makes comparison and reproduction much, much easier.
Okay, so MLflow tracks the experiments. But when logging the model itself with MLflow.PyTorch.log model, there's this optional model signature. You mentioned this is really important for production. Why?
This is a fantastic feature for bridging the gap between training and deployment. The signature isn't just metadata. It's a formal definition, a schema of your model's expected inputs and outputs.
Schema, like data types and shapes.
Exactly. Names, types, shapes. Think of it as a contract. When you deploy this model later, the serving system can use this signature to automatically validate incoming prediction requests.
Ah, so it checks if the data format matches what the model expects before even running the model.
Precisely. It catches malform requests early, prevents runtime errors caused by unexpected input data, and makes the whole deployment much more robust. It turns your saved model file into a self-describing, validated asset.
That's a huge step towards reliable production systems. Okay, but what if things go wrong during training or inference? The model behaves weirdly, loss explodes, accuracy flatlines. How do you debug inside that black box?
That's where PyTorch hooks come in. They are incredibly powerful for inspecting the internals of your model without having to modify its source code directly.
Hooks, like callback functions.
Kind of, yeah. You can attach them to any nn.Module or even individual tensors. They get triggered automatically during the forward or backward pass, letting you run your own custom code at that point.
So a forward hook, what would you use that for?
Register forward hook runs right after a module's forward method completes. You could use it to grab the output activations of a layer, log their statistics, min, max, mean, or even plot a histogram. Super useful for spotting issues like dying ReLUs where neurons get stuck outputting 0 or exploding activations.
See what's happening layer by layer. And backward hooks for gradient problems.
Exactly. Register hook on a tensor runs when the gradient for that specific tensor has been computed during the backward pass. This is invaluable for diagnosing vanishing or exploding gradients. You can print the gradient values, check if they're getting too small or too large as they flow backward through the network.
Okay, that sounds way better than sprinkling print statements everywhere. But wait, doesn't PyTorch usually discard intermediate gradients to save memory? How do hooks compare to using a Autograd on intermediate tensors?
Excellent question. You can use .retainegrad to force PyTorch to keep those intermediate gradients, but on large models, that can balloon your memory usage and potentially cause out-of-memory errors.
Right.
Hooks are much more memory efficient. The backward hook receives the computed gradient as an argument. You can inspect it, log it, whatever you need to do, right there and then before the Autograd engine frees that memory. It lets you observe the gradients without needing to store them all indefinitely. Much more scalable for big models.
Hooks for debugging. Got it. Okay, phase 3. We've trained a model, tracked it with MLflow, debugged it with hooks. It works, but it's not quite ready for the real world yet. You mentioned an optimization gauntlet. What's that about?
Yeah, a raw trained model is often too big, too slow, or too power hungry for production deployment, especially on edge devices or mobile. The optimization gauntlet is about applying techniques to make it smaller, faster, and more efficient without sacrificing too much accuracy.
What are the main techniques in this gauntlet?
Typically, we look at model pruning, model quantization, and knowledge distillation.
Okay, let's break those down. Model pruning sounds like trimming the fat.
That's exactly what it is. Removing redundant parameters, weights, or biases, or even entire structures like filters or attention heads.
Are there different ways to prune?
Yeah. Unstructured pruning zaps individual weights, making the weight matrices sparse. This can give high compression, but often needs special hardware or libraries to actually speed up inference. Structured pruning removes entire blocks, like whole filters in a CNN or rows in a matrix. This results in a smaller, dense model that's usually faster on standard hardware. Often, pruning globally across the model works better than layer by layer.
How do you actually do it?
Usually you apply a binary mask to zero out the pruned weights during or after training, and then you can make the pruning permanent, actually removing the parameters to get the smaller model.
Okay, so pruning shrinks the model. What about model quantization?
Quantization is about reducing the numerical precision used to represent the model's weights and sometimes activations. Most commonly, going from 32-bit floating point, FT32, down to 8-bit integer, INT8.
Why do that? What are the benefits?
Big ones. You typically get about a 4x reduction in model size and memory usage. And on hardware that supports INT8 operations well, like many modern CPUs and specialized accelerators, you can see inference speedups of 2x to 4x.
4 times smaller and faster. That's huge. Are there different ways to quantize?
Yes, with different trade-offs. The simplest is dynamic quantization, done post-training. You quantize the weights offline, but the activations are converted to INT8 on the fly during inference. Works well for models where activation ranges vary a lot, like LSTMs or transformers.
Okay, simplest. What else?
Static quantization, also post-training. Here, you quantize both weights and activations offline. This requires an extra step called calibration, where you run the model on some representative data to figure out the typical range of activations for each layer. Usually gives better performance than dynamic.
Calibration, like figuring out the scale factors.
Exactly. And the third main type is quantization-aware training, QAT. This is the most involved, but often gives the best accuracy.
How does QAT work?
You actually simulate the effects of quantization during the training or fine-tuning process itself. PyTorch has tools to insert fake quantization nodes into the graph. This lets the model learn to be robust to the lower precision. You train it to handle the quantization noise.
So QAT gives the model a heads up about the quantization coming. And the third technique, knowledge distillation. Teacher and student models. Sounds cool.
It is pretty cool. The idea is you have a large, powerful, accurate teacher model that's already trained. Then you train a much smaller, faster student model.
How does the student learn?
It learns in two ways. It learns from the normal ground truth labels, like any model. But it also learns to mimic the output distribution of the teacher model specifically, the teacher's logits, the raw scores before the final softmax.
Why mimic the logits?
Because those logits contain richer information than just the hard label. The teacher might be very confident it's a cat, but its logits might also show a tiny probability for dog and almost 0 for car. This subtle information, sometimes called dark knowledge, tells the student about relationships between classes.
Ah, the teacher transfers its nuanced understanding.
Exactly. The student learns these subtleties and often ends up much more accurate than if it had only trained on the hard labels, getting closer to the teacher's performance but in a much smaller package. The loss function combines the standard loss with a distillation loss, often using a temperature scaling factor to soften the teacher's outputs and make the transfer easier.
Fascinating. Okay, pruning, quantization, distillation. How do you choose?
It depends entirely on your production constraints. Need maximum compression and have special hardware, maybe unstructured pruning. Need a smaller, dense model for standard hardware. Structured pruning, easy speedup for RNS transformers. Dynamic quantization, better speedup for CNNs. Static quantization, highest accuracy with quantization. QAT, if you can afford retraining. Need to shrink a big, accurate model. Distillation, you pick the tool for the job based on accuracy needs, latency targets, model size limits. Great overview of the optimization options. So model is optimized. Now we need to package it for deployment. Why can't we just, ship the Python code in .pt file?
Well, your Python PyTorch model relies on the Python interpreter, the PyTorch library, maybe specific versions, their custom code structure. It's not self-contained or easily runnable in many production environments like a C++ backend, a mobile app, or an edge device. You need to serialize it into a more portable, high-performance format.
Right. Makes sense. And PyTorch's native solution is TorchScript. Yep. TorchScript aims to create serializable and optimizable models from PyTorch code. It has two main ways of doing this: tracing and scripting.
Okay, tracing first. How does that work?
Tracing, torch.jit.trace, is simple. You feed your model a sample input, PyTorch executes the model, and it records all the operations it sees into a static graph representation.
Simple, but what's the catch?
The big catch is control flow. If your model has if statements or loops that depend on the values of the input tensors, tracing only records the path taken for the one sample input you provided. It won't capture the other branches or dynamic behavior.
Ah, so it might work for that one input but fail on others.
Exactly. It's fine for models with very static architectures like many CNNs, but risky for anything dynamic.
So that's where scripting comes in.
Right. Scripting, torch.jit.script, actually analyzes and compiles your Python model code itself, understanding a subset of Python, including control flow, like ifs and loops. It converts your potentially dynamic Python code into a static TorchScript graph representation that captures the logic.
More robust for dynamic models, but maybe harder to get working.
It can be, yeah. Your code needs to stick to the subset of Python that TorchScript understands. Sometimes you need to refactor things a bit.
Why have both tracing and scripting? Seems complicated.
It's really a direct result of PyTorch's define by run nature. Because there's no static graph to begin with, tracing offers an easy way to capture one execution path. Scripting offers a more powerful way to capture the intended logic, including dynamic parts. They serve different needs. Though the PyTorch team is working on torch.export, a newer API aiming to unify and improve this whole process.
Good to know. What about alternatives? ONNX comes up a lot.
ONNX, the Open Neural Network Exchange. It's not PyTorch specific, it's an open standard format for ML models.
What's the main advantage of using ONNX?
Interoperability is the key word. You export your PyTorch model to RNNX format, torch.onnx.export, and then that ONNX file can be run by many different inference engines. Like Microsoft's ONNX runtime, NVIDIA's Tensor, which optimizes heavily for NVIDIA GPUs, Intel's OpenVINO for Intel hardware, and others. It gives you flexibility to choose the best runtime for your target hardware, independent of the training framework.
So you train in PyTorch, export to ONNX, deploy anywhere?
That's the idea. But crucial step, always verify the exported ONNX model. Load it back, check it with onnx.checker.check model, and run some sample inputs through both the original PyTorch model and the ONNX model to make sure the outputs match numerically. Don't skip verification.
Verification is key. Okay, optimized serialized model in hand, time to serve predictions. We have TorchServe, FastAPI, NVIDIA Triton. How do you pick the right tool?
It really depends on your needs. Ease of use, performance, flexibility. TorchServe is the official PyTorch option.
What does it offer?
It's built for production. Gives you REST and gRPC endpoints out of the box, handles model versioning, logging, metrics, even automatic batching of incoming requests to improve throughput. You package your model and a handler script into a .mar archive file. Pretty streamlined for PyTorch models.
Okay. Then there's FastAPI. It's a general Python web framework, right? Not just for ML.
Correct. But it's become super popular for building custom ML APIs because it's fast, modern, and easy to use.
How would you use it?
You'd load your TorchScript or ONNX model inside your FastAPI application code. Then you define your API endpoints, like predict, and the logic for pre-processing input, running inference, and post-processing the output. It uses Pydantic for easy data validation of requests. Gives you tons of flexibility for custom logic around your model.
But you need to handle scaling and stuff yourself.
Yeah, you typically run it with an ASGI server like Uvicorn, maybe put it in a Docker container, and use standard infrastructure tools like Kubernetes for scaling.
Got it. And the third one, NVIDIA Triton Inference Server? Sounds heavy duty.
It is. Triton is designed for high-performance inference, especially optimized for NVIDIA GPUs, though it supports CPUs too. Its biggest strength is its versatility.
How so?
It can serve models from pretty much any major framework, PyTorch, be it TorchScript or ONNX, TensorFlow, ONNX directly, TensorRT, often multiple models concurrently, even on the same GPU.
Wow, multi-framework support. How do you set it up?
It uses a specific model repository folder structure. For each model, you need a config.pbtxt file describing its inputs, outputs, and which backend, like PyTorch or on Nix runtime, to use. Clients interact with it using a dedicated client library. It's built for really high throughput scenarios, but has a steeper learning curve than, say, FastAPI.
Okay, quick summary. TorchServe for PyTorch native, managed serving. FastAPI for flexible, custom APIs you scale yourself. Triton for maximum performance, multi-framework, GPU-heavy deployments.
That's a good way to put it.
Clear choices there. Now, scaling up not inference, but training. We talked about single GPU limits. What's the go-to solution for bigger models or datasets?
Distributed training. And while PyTorch has data parallel, DP, the real standard, the one you should almost always use for serious work, is distributed data parallel, DDP.
BP versus DDP.
Yeah.
What's the core difference and why is DDP better?
Data parallel is simpler. Conceptually, it splits a batch across GPUs on one machine, but it runs everything through one main Python process. This hits bottlenecks with Python's GIL, and the main GPU often does extra work coordinating, leading to unbalanced load.
So DP doesn't scale well.
Not really, no. DDP is fundamentally different. It's a multi-process approach. You launch a separate Python process for each GPU. Each process controls its own GPU.
No GIL bottleneck then.
Exactly. And instead of one GPU gathering everything, DDP uses efficient collective communication operations like ring, all reduced behind the scenes, to average the gradients calculated by each process after the backward pass. It's much faster and scales beautifully, even across multiple machines.
Okay, DDP is the way. How do you set it up? What are the key steps?
First, the setup. Each process needs to initialize communication using torch.distributed.init process group. You'll specify a backend NCL is standard and fastest for NVIDIA GPUs, and each process gets a unique global rank and a local rank, its GPU index on the machine.
Okay, initialize the group, then data.
Crucial part, you need to make sure each process gets different data. Otherwise, they're all doing the same work. The torch.utils.data.distributed. Distributed sampler is designed for this. You wrap your data set with it, and it automatically gives each process a unique slice shard of the data for each epoch.
Smart. So each GPU sees different examples. What about the model?
Simple. You just wrap your existing nn.Module with DDP, model DDP, model devices local rank. DDP takes care of broadcasting the initial model weights from rank 0 to all other processes and handles the gradient synchronization automatically during backward.
Seems quite manageable. Anything special about the training loop or saving?
The loop itself looks very similar, but saving checkpoints needs care. To avoid multiple processes writing the same file and causing race conditions, you typically have only the main process, rank 0, save the model checkpoint.
Only rank 0 saves. Got it. That makes distributed training seem much more approachable. Okay, last big section. Closing the loop with MLOps. Managing the whole lifecycle systematically. Let's start with the MLflow model registry for versioning. What problem is this solving day to day?
Imagine your team retrains a model every week with new data. You quickly end up with dozens of model files. Which one performed best? Which one is currently in staging? Which one is running in production? Which experiment run produced this specific file? It becomes chaos.
Yeah, tracking that manually is tough.
The model registry provides a central place to manage all these registered model artifacts. It gives you versioning lineage back to the training run and ways to manage the model's journey through different stages like development, staging, and production. It's the single source of truth for your production-worthy models.
How does it work in practice? You finish an MLflow run.
Right. If the run was successful, you use MLflow.register model to take the saved model artifact from that run and formally register it under a specific name, like my transformer. Each time you register under that name, MLflow creates a new auto-incrementing version number version 1, version 2, etc., linked directly back to the originating run.
Okay, clear versions and lineage. How do you manage staging versus production? I heard stages are deprecated.
That's right, the old stage concept, staging, production, archived, is being replaced by a more flexible system using aliases and tags. Aliases are like mutable pointers or labels you can assign to specific model versions.
Like nicknames.
Exactly. You might create an alias called champion and point it to version 5, which is your current production model. You could have another alias challenger pointing to version 7, which is undergoing tests. Tags are just key value pairs for storing arbitrary metadata, like validation status, passed, or trained on dataset, June 2025.
Ah, so the deployment system just asks for the model version currently pointed to by the champion alias.
Precisely. An inference service might request models.myTransformerChampion. The data science team can update which version the champion alias points to via the MLflow UI, or API, completely independently of any infrastructure changes.
That decouples model promotion from deployment rollout. Very neat. It really makes the registry the central hub.
It does. It's a core MLOps component for managing the model lifecycle.
Okay, final piece. Automating the whole pipeline. CLCD with something like GitHub Actions. Why is this automation so important?
It's about robustness, repeatability, and speed. Continuous integration, CI, automatically tests your code changes, ensuring you don't break things. Continuous deployment, CD, automates the process of getting your trained and validated model out into production safely and quickly. Automation removes manual steps, reduces errors, and lets you iterate faster.
And GitHub Actions integrates this right into your repo.
Yeah, it's built into GitHub. You define workflows and YAML files directly in your repository. These workflows can be triggered by events like code pushes, pull requests, or even on a schedule or manually.
Can you walk through a simple MLOps pipeline example using GitHub Actions for our PyTorch project? Put all the pieces together.
Sure. You might have a few jobs in your workflow. First, a CI job. Triggered on pushes or pull requests, it would check out the code, set up the Python environment, run linters for code quality, and execute unit tests. Basic code health checks.
Okay, standard software CI.
Then, maybe a training job. This could be triggered manually, or perhaps automatically after CI passes on the main branch or on a schedule. This job runs your actual training script.
The script that uses MLflow.
Exactly. The script logs the experiment to MLflow, evaluates the model, and if it meets the criteria, it registers the new model version in the MLflow model registry.
Training and registering automated. What next?
Finally, a CD job. This might be triggered manually after a model version is approved, or maybe automatically when, say, the challenger alias gets promoted to champion. This job would check out deployment-related code, use the MLflow client to download the specific model version needed, e.g. the one tagged champion, from the registry.
Pulls the right model artifact.
Builds a production Docker image containing the model and the serving application, like your Fast API app, pushes that image to a container registry, like Docker Hub or AWS ECR, and could even trigger an update to your deployment environment, like Kubernetes or a cloud function.
Wow. So it automates the whole path from code commit or model approval right through to a deployed running service.
That's the goal of a mature MLOps pipeline, automation for consistency and speed.
Incredible. We have really covered a massive amount of ground today. We went from the absolute basics tensors nn.Module right through building complex architectures like the transformer, navigating that whole optimization gauntlet, serialization, deployment options, scaling up training with DDP, and finally tying it all together with MLOps, experiment tracking, and CI/CD.
It's a lot, but the key thing, I think, is seeing how these pieces connect. That's where the deep experience really comes from. It's not just knowing the syntax for each part in isolation.
Right, it's understanding the why.
Yeah, like understanding how using pin memory and non-blocking in your data loading prevents your GPU from stalling, which is especially critical when you scale up to DDP with multiple GPUs.
Yeah.
Or seeing how that model signature you logged with MLflow provides the contract that makes your Fast API deployment robust against bad input data.
Or why Torch script needs scripting, not just tracing, to handle the dynamic Python control flow that makes PyTorch so flexible for research in the first place.
Exactly. Or how DDP fundamentally solves the scaling limitations of DP by moving to multiprocessing. It's those connections, theory to practice, development to operations, low-level details to high-level architecture that make the difference.
That really captures the essence of moving beyond the tutorials. The PyTorch ecosystem is huge, it's always evolving, but these principles we've talked about today, they provide a really solid foundation, connecting the fundamentals to production, understanding the trade-offs, automating the process. That's durable knowledge. And so, for everyone listening, after this deep dive charting the course from basics to production, what aspect of this whole journey, from tensor mechanics to MLOps automation, are you going to dig into next?